We live in a world drowning in data. Videos, photos, messages, our digital footprint expands every day. Storing it all requires massive data centers, consuming energy and space. But what if we could store information in something far smaller and more durable? What if that something was already inside us? That's the promise of DNA storage. Imagine all the data in the world held in a container the size of a sugar cube. DNA, the blueprint of life, is also a remarkably efficient way to store information. It's incredibly dense, holding billions of times more data than our current hard drives, and it's incredibly durable, lasting for thousands of years. This isn't science fiction, it's happening now. Scientists are encoding digital information into DNA strands, creating a new generation of storage technology. This revolutionizes how we preserve our digital legacy. Let's explore how this mind-blowing technology works. To understand DNA storage, we need to understand DNA itself. Imagine a long, twisted ladder. The rungs of this ladder are made of 4 chemical bases, A, T, C, and G. These bases are the alphabet of life. The sequence of these bases determines the genetic instructions for building and maintaining an organism. Think of it like a digital code, but instead of zeros and ones, we have A, T, C, and G. The beauty of DNA is its density. A single gram of DNA can theoretically store an unbelievable amount of digital data, equivalent to billions of gigabytes. That's more data than all the world's hard drives combined. And unlike hard drives, which degrade over time, DNA can last for millennia under the right conditions. So, how do we go from digital ones and zeros to the A, T, C, and G of DNA? It's all about translation. We use a conversion system to represent digital data using the 4 DNA bases. Think of it like a secret code. We assign a unique combination of DNA bases to represent each 1 and 0 in the digital code. For example, 00 might become AT, 01 might become GC, and so on. This process allows us to convert any digital file, a photo, a song, or even an entire movie, into a string of DNA molecules. This string of DNA then becomes the storage device for that information. Section 4. Building the DNA computer. Hardware and software. Storing data in DNA is one thing, but how do we read and write it? That's where specialized hardware and software come in. On the hardware side, we need DNA synthesizers to write the data onto DNA strands and DNA sequencers to read the data back. Think of these as the writers and readers of the DNA storage system. On the software side, sophisticated algorithms are needed to translate between digital code and DNA sequences. These algorithms ensure the data is stored accurately and can be retrieved without errors. Think of this as the operating system of the DNA computer, managing and accessing the data. Section 5. From labs to life, scaling up DNA storage. DNA storage is still in its early stages. However, the potential is enormous. Imagine a future where data centers are the size of rooms, not warehouses. We can store the entire history of human knowledge in a tiny vial. Data loss becomes a thing of the past. Scaling up DNA storage involves overcoming several challenges. We need to make DNA synthesis and sequencing faster, more affordable, and more accessible. However, researchers are making rapid progress. As the technology matures, we can expect to see DNA storage move from specialized labs to everyday applications. Section 6. The future of data, a DNA revolution. DNA storage is more than just a technological leap, it's a paradigm shift in how we think about data. It offers a future where data is stored sustainably, efficiently, and for millennia. This technology has the potential to revolutionize everything from archival and data centers to personalized medicine and even space exploration. Imagine sending vast amounts of data into space, stored within the very fabric of life itself. The future of data is written in the language of life, and it's a future filled with incredible possibilities.